Hello, welcome to the course PH5 BO6 Electrodynamics 2. The contents of today's lecture is taken from Fundamentals of Magnetism and Electricity by D.N. Vasudeva. We'll continue to discuss topics from Chapter 22, Alternating Current Circuits. In the previous class, we have analyzed the flow of AC current through an inductor circuit as well as a capacitor circuit. In the case of inductor, we have seen that the applied voltage leads the current by a phase angle pi by 2, and in the case of capacitor, voltage lags the current by the same phase angle pi by 2. Today let's analyze the AC flow through an LR circuit where an inductor of inductance L and an ohmic resistor of resistance R are connected in series to an AC voltage. So in the previous classes, we have tried to answer the question for a given AC voltage E equal to E naught sine omega t, what is the corresponding AC current? Today, let's try to answer the converse question. For an AC current I equal to I naught sine omega t to flow through a given circuit, what should be the applied AC voltage? As always, starting point is writing down the EMF equation. We know that out of the applied voltage E, a part of it is utilized to overcome the back EMF associated with the inductor minus L into di by dt, and the remaining part drop across the resistor. So there are two voltage components, one associated with the inductor VL and the other one associated with the resistor VR. So the total applied EMF E can be written as sum of VR, which is I into R, plus VL, which is L into di by dt. Since the instantaneous value of current I equal to I naught sine omega t, from that I can write di by dt equal to I naught omega cos omega t. In the EMF equation now substitute for I and di by dt, it becomes applied voltage E equal to I naught R sine omega t plus I naught L omega cos omega t. I naught is common, take it outside. Also, let's take out a common factor, square root of R square plus L square omega square. Now the equation becomes I naught into square root of R square plus L square omega square multiplied by, in the first term, R divided by square root of R square plus L square omega square sine omega t plus L omega divided by square root of R square plus L square omega square cos omega t. Let's try to simplify this equation. In the first term, define R divided by square root of R square plus L square omega square as cos phi, where phi is some phase angle. And in the second term, call this term L omega divided by square root of R square plus L square omega square as sine phi. Now this equation gets simplified as E equal to I naught into square root of R square plus L square omega square cos phi sine omega t plus sine phi cos omega t. Now the term inside this bracket is sine omega t plus phi. Now, what does this term square root of R square plus L square omega square mean? So R is the resistance of the ohmic resistor and L omega is the reactance or resistance of the inductor. So this term essentially gives you the total resistance offered by the LR circuit towards the AC flow. So this total resistance or the effective resistance is known as impedance. So remember, we have three different terms. One is resistance, which is typically used in the context of DC flow. And there is reactance, which is used for AC flow. And when you have multiple electrical components, the total resistance or total reactance is represented by the term impedance. The inverse of impedance is known as admittance, which is denoted by the symbol Y. Now coming back to the EMF equation, so here if you look at the constant term here, I have the peak current I naught multiplied by the total resistance, which is the impedance. Current into resistance is nothing but voltage, so peak current into resistance I can call as peak voltage E naught. Now the EMF equation becomes E equal to E naught sine omega t plus phi. If you compare the voltage expression and the current expression, you can easily make out that the applied voltage in the case of a series LR circuit leads the current by a phase angle phi. Alternatively, you can say the current lags the applied voltage by the same phase angle phi. Now what is the value of phi? From these two expressions, I can write sine phi by cos phi, which is tan phi equal to L omega divided by R, from which I can write phi equal to tan inverse L omega by R. And if you look at the values of phi, it ranges between 0 and pi by 2. Let's quickly plot the waveforms here. So as always, you can draw the voltage as E naught sine omega t, and if you take that, current lags behind the voltage, so current starts somewhere down the line. If you look at the starting point, you can see that the voltage is leading over the current, or current is lagging behind the voltage. So even though here the expression is E naught sine omega t plus phi, when I just plotted E naught sine omega t, and current I plotted as I naught sine omega t minus phi. So in any case, you need to maintain the phase relation between these 2 points. Okay. So if you quickly compare this with the inductor circuit, there you have seen the same kind of waveform. The voltage starts from the 0 point, but the current started from the negative peak point, right? So here it need not be always starting from the negative point. If the voltage is starting from 0, current could start anywhere between 0 point and the negative peak, right? That's the meaning of phi ranges between 0 and pi by 2. So when phi is 0, current also starts from the same 0 point. When phi is pi by 2, current starts from the negative peak, as in the case of inductor circuit. For any other case, it starts from any other in between points. Now, if you take the ratio of voltage and current, so E by I is E naught sine omega t plus phi divided by I naught sine omega t, which is square root of R square plus L square omega square multiplied by sine omega t plus phi divided by sine omega t. Normally, in the case of a DC circuit, if you consider this ratio E by I, voltage by current is a constant known as resistance, right? So this is what the Ohm's law says. But here we can see that in the case of an AC circuit, E by I is not a constant. This is a function of time, right? Here when time varies, this ratio is also varies. Therefore, the instantaneous values of voltage and current do not obey Ohm's law. On the other hand, if you take the ratio of E naught and I naught, the peak values, you will know that E naught by I naught is nothing but the impedance square root of R square plus L square omega square, which is a constant for a given circuit. So in the case of AC circuits, only E naught and I naught obey Ohm's law, whereas the instantaneous values E and I do not obey the Ohm's law. You can also represent the phase relation using the vector method. So you have two voltage components here, one associated with the resistance VR, which is IR, and one associated with the inductor VL, which is I into L omega. We know that in the case of an ohmic resistor, current and voltage are in phase. So this voltage component is in phase with the current. So you can call this as the in phase component. So we are going to take this component as our reference direction. Then in the case of an inductor, we know that voltage leads the current by pi by 2. So which is represented by this counterclockwise angle of pi by 2 with respect to the in phase component. Since VL is out of phase by pi by 2 with respect to current, I call this as the out of phase component. So I have two components, the in phase component and the out of phase component. And the net voltage is the vector sum of these two components, so which is represented by this arrow here. The magnitude of this is current I multiplied by total resistance, which is given by the impedance square root of R square plus L square omega square. And what is a phase relation? We know that the net voltage leads the current by an angle phi. So this is represented by this counterclockwise angle of phi between the in phase component and the net voltage component. Also, in the previous class, when we discussed about AC flow through an inductor, I have said that if you look at the waveform, if you analyze successive quarter cycle, you will see that in one quarter cycle power is positive and in the next quarter cycle power is negative. So the power is continuously transferred between the source and the inductor, and if you make sure that the internal resistance of the inductor is negligible, then you can switch power between source and inductor without any power loss. That's why we said this is a much more effective way of restricting AC flow compared to an ohmic resistor, right? Since there is no power loss, we can call this particular component as the wattless component. Remember, the unit of power is watt. So to indicate that there is no power loss across this component, we call this as the wattless component. Now coming back to the definition of cos phi, this is defined as R divided by square root of R square plus L square omega square. And if you recollect my previous classes, I said whenever there is a resistor, it always leads to a power loss due to Joule's heating or heat dissipation, right? So R is the reason behind power dissipation. So if the value of R is higher, there is more power dissipation or power loss. When the value of R is lower, there is less power dissipation or less power loss. So since the power dissipation is determined by this factor, I will also call this as the power factor of the circuit. Now the value of the power factor ranges between 0 and 1. If the ohmic resistance in the circuit is 0, then power factor is going to be 0. And if the value of resistance is infinity, then you can neglect L square omega square because R square is going to be much higher than this term. So you have R divided by square root of R square, which is going to be 1. So these are the extreme values, endpoints, but usually you are not going to get these two values in any practical circuit because it's impossible to construct a practical circuit with 0 ohmic resistance. You know that, right? For any electrical component we use, there is a finite amount of internal resistance. So 0 is impossible. You can get a value very close to 0. Similarly, you can never construct a circuit with infinite resistance, right? If you want to make the resistance infinity, you need to break the circuit. There is an air gap that gives you an infinite resistance. But the moment you break the circuit is functionless, right? So for any working circuit, the power factor is going to be between 0 and 1. So that's about the analysis of an LR circuit. In the same way, we will quickly analyze the AC flow through a CR circuit where the capacitor of capacitance C is connected in series to a resistor of an ohmic resistor of resistance R. Here also we will try to answer the converse question. For an AC current I equal to I naught sine omega t to flow through a series here circuit, what should be the applied AC voltage? So we know the value of the current. We want to find out what is the value of the applied voltage. As always, write down the EMF equation. There are two components for the voltage, one across the capacitor VC and one across the resistance VR. And the value of VR is IR, and the potential drop across capacitance is Q by C, where Q is the charge stored in the capacitor. So the total voltage E equal to IR plus Q by C. We know that I equal to I naught sine omega t. This is given. In terms of charge, I can write I equal to dq by dt. And from this, I can write Q equal to integral of I naught sine omega t dt, which is nothing but minus I naught by omega cos omega t. So once I know the expression for current and charge, I can substitute this back into the EMF equation. So the equation becomes E equal to I naught R sine omega t minus I naught by C omega cos omega t. I naught is common. I am also going to take out a common factor, square root of R square plus 1 by C square omega square. So when I do that, the EMF equation becomes E equal to I naught into square root of R square plus 1 over C square omega square multiplied by R divided by square root of R square plus 1 over C square omega square sine omega t minus 1 over C omega divided by square root of R square plus 1 by C square omega square cos omega t. Equation looks cumbersome. We need to simplify it. You know the drill, right? Call this factor as cos phi and this factor as sin phi. Now the equation becomes E equal to I naught into square root of R square plus 1 over C square omega square cos phi sin omega t minus sin phi cos omega t, which is nothing but I naught into square root of R square plus 1 over C square omega square sin omega t minus phi. Now look at this term. So the first term is the resistance of the ohmic resistor. Second term is the resistance of the capacitor. So this term gives you the total resistance offered to the AC flow by the CR circuit. The total resistance we call as impedance Z. If you take inverse of that, you get admittance of the circuit. And this term, this is the peak current multiplied by the total resistance, which is nothing but the peak voltage. So the expression for the applied voltage is E equal to E naught sine omega t minus phi. If you compare this with the current expression, you can easily make out applied voltage lags the current by a phase angle phi, or current leads the applied voltage by a phase angle phi. Now what's the value of phi? Calculate sin phi by tan phi, sin phi by cos phi, which is tan phi. This is equal to 1 over C omega by R, or phi equal to tan inverse 1 over C omega divided by R. And just like the previous case, its value ranges between 0 and pi by 2. So let's plot the waveforms here. So instead of plotting E naught sine omega t minus phi, I plot E naught sine omega t. This is just to make the analysis standard. Every time we plot E naught sine omega t here, this is our reference. And current leads the applied voltage, right? So current I plot as I naught sine omega t plus phi. Okay. So just make sure that the phase relation is maintained. That's it. Okay. So from the starting point, if you look at the starting point, this is very clear. Current leads over the voltage. Quickly compare this with the capacitor circuit. So in the case of capacitor circuit, you have seen that voltage always starts from the 0 position, and there the current started from the positive peak. Now here voltage starts from the 0 position and current start anywhere between the 0 point and the peak point. So if phase angle phi equal to 0, both current and voltage start from the same 0 point. On the other hand, if it is pi by 2, then just like the capacitor circuit, voltage start from the 0 point and current start from the peak point. For any other case, current starts from an in-between point, anywhere between this point and this point. Coming to the vector diagram, we have two voltage components here, one across the resistance VR and one across capacitance, which is BC. And the VR component is given as current I multiplied resistance R, and VC component is current I multiplied by 1 by C omega. Sorry for the typo here, the current I is missing here. So this is I into 1 over C omega. This is the in-phase component, this is the out-of-phase component. If you recollect, in the case of capacitor, voltage lags the current by pi by 2. So this is indicated by a clockwise angle of pi by 2. Remember, clockwise angle indicates an angle of lag. If you take the vector sum of these two components, you get the total voltage I into square root of R square plus 1 by C square omega square, current multiplied by total resistance or impedance. And what is the phase relation? Voltage lags the current by phi, right? So this is the total voltage. It lags the current, which is represented by the in-phase component by an amount phi here. So the angle of the clockwise angle of phi indicates that the voltage lags the current by phi. So that's about the analysis of AC flow through an LR circuit and a CR circuit. In the next class, we will try to understand the behavior of AC flow through an LCR circuit. Thank you.